What are two common use cases of generative AI? Select two answers. A. Creating text summaries of complex documents. B. Manually coding application logic in JavaScript. C. Generating new documents as a starting point for projects. D. Performing rule-based data validation. The correct answers are A. Creating text summaries of complex documents. C. Generating new documents as a starting point for projects. Let's take a moment to explain why those are the correct answers. First, creating text summaries of complex documents is a classic use case of generative AI. Think about lengthy legal contracts or research papers. Generative AI can analyze the text, understand its context, and produce a concise summary, helping users quickly grasp the key points. Next, generating new documents as a starting point for projects is another powerful example. For instance, AI can draft a business proposal, a blog post, or even an email. The user then edits and refines it, which speeds up the creative process significantly. On the other hand, manually coding application logic in JavaScript is a task performed by developers. While AI tools like GitHub Copilot can assist, the act of manually coding isn't something generative AI takes over entirely. Similarly, performing rule-based data validation is a predefined deterministic process. It doesn't involve any content generation or creative reasoning, so it falls outside the scope of generative AI's strengths. So generative AI shines where content needs to be created, summarized, or reimagined, not in rule-based logic or manual tasks. For each statement below, indicate whether the answer is true or false. Speech recognition converts spoken language into text. True. Speech synthesis requires the user to speak into the system. False. AI speech systems can ignore background noise and detect interruptions. True speech translation converts text from one language to another. False. Let's go over each of these to understand the reasoning behind the correct answers. Speech recognition converting spoken language into text is absolutely true. This is the core function of speech-to-text technology, where your voice is transcribed into written words, something we see in virtual assistants or transcription apps. Now, the second statement says, speech synthesis requires the user to speak into the system, but that's false. In reality, speech synthesis is about converting text into spoken audio. It's a text-to-speech process, not the other way around, so your voice input isn't required at all. Next, it's true that AI speech systems can ignore background noise and detect interruptions. Many modern AI-powered systems are trained to filter out unwanted noise and focus on the speaker, which makes them more effective in real-world environments like call centers or busy homes. Lastly, the idea that speech translation converts text from one language to another is false. What's actually happening in speech translation is that spoken audio in one language is captured, transcribed, translated, and then spoken back in the target language. So it's converting audio to audio, not just text. So all four of these give us a great look at how speech technologies differ and how AI enhances them in real use cases. Fill in the blanks by selecting the correct options from the drop-down menus. Chatbots that handle FAQs and predictable questions can be built using simple NLP models, whereas more complex, open-ended conversations may require generative AI. Let's walk through why these answers make the most sense. To begin with, when you're building chatbots to answer FAQs or handle very structured, predictable interactions like checking account balances or booking appointments, simple NLP models are usually enough. These models don't need to be creative. They just need to map fixed inputs to known responses efficiently. On the other hand, when you want your chatbot to engage in more flexible, open-ended conversations, think of customer support that involves storytelling, handling vague questions, or offering nuanced suggestions. You need generative AI. These models can produce varied and contextually rich responses, allowing for much more natural and dynamic exchanges. Other options like speech recognition, image classification, or rule-based logic don't apply here. For example, speech recognition is about converting voice to text, not about the language model itself. Rule-based logic is static and doesn't adapt or generate responses. And image classification and object detection belong to the vision domain, not natural language processing. So, when choosing between models, it really comes down to the complexity and variability of the conversation you expect your chatbot to handle. You are comparing two regression models based on their ability to predict daily ice cream sales. Model A has a lower root mean squared error RMSE than Model B. What does this indicate about Model A? Select one answer. A. It explains more variance in the dataset. B. It fits the data less accurately than Model B. C. It has more consistent errors in prediction. D. It has smaller prediction errors on average. The correct answer is D. It has smaller prediction errors on average. Let's go ahead and explain why that's the case. When you're comparing regression models, RMSE is one of the most common metrics for evaluating performance. A lower RMSE tells us that the model's predictions are on average closer to the actual values. So if Model A has a lower RMSE than Model B, it means Model A's predictions are generally more accurate. Now, option A refers to variance explained in the dataset, which is measured using the R-squared metric, not RMSE. So that choice doesn't apply here. Option B says Model A fits the data less accurately, but that's the opposite of what a lower RMSE indicates. A smaller error actually points to better fit. As for option C, consistency in prediction errors is more about the spread or variability in error, not the magnitude. RMSE captures the average size of the errors, not how consistently those errors occur. So overall, RMSE helps you judge how close the model's predictions are to reality, and in this case, Model A clearly performs better than Model B. For each statement below, indicate whether the answer is true or false. The output of a logistic regression model is a probability between 0 and 1. True. Binary classification models predict numeric values like regression. False. Precision is the percentage of predicted positives that are actually positive. True AUC values less than 0.5 indicate better than random performance. False. Let's walk through each of these and explain what they really mean. The first statement is true. Logistic regression outputs a probability score between 0 and 1, representing the likelihood that a data point belongs to a particular class. Typically, this score is then thresholded, say at 0.5, to make a final classification. Now, the second statement is false. Binary classification doesn't predict continuous numeric values like regression does. Instead, it predicts discrete categories, like whether an email is spam or not spam. While logistic regression does use numeric output internally, the end goal is categorical classification. Moving on, the third statement is true. Precision tells us how many of the positive predictions made by the model were actually correct. So if your model says 10 items are positive and 8 really are, your precision is 80%. Finally, the last statement is false. AUC, or area under the ROC curve, measures how well a model distinguishes between classes. And an AUC of 0.5 is what you'd expect from random guessing. Values below 0.5 actually indicate worse than random performance, not better. So understanding these metrics helps you better evaluate and improve your classification models in practice. Fill in the blanks by selecting the correct options from the drop-down menus. In a confusion matrix, the diagonal cells represent the correct predictions made by the model. Let's break down what this means and why it's correct. The diagonal in a confusion matrix runs from the top left to the bottom right. It includes all the instances where the model's prediction exactly matches the actual class label. So if a model is classifying animals and predicts dog when the actual label is also dog, that prediction falls on the diagonal. These diagonal cells are referred to as correct predictions because they reflect true positives in binary classification or correctly classified labels in multi-class settings. Every off-diagonal entry, by contrast, represents a mistake, either a false positive or false negative. Other terms like vertical, incorrect, or misclassified don't describe this concept. Those would refer to cells that represent errors, and probability-based doesn't apply here, since confusion matrices use hard class labels, not probability scores. So if you're ever analyzing a confusion matrix, just look along the diagonal to see how many predictions your model got right. What is the goal of a multi-class classification model? Select one answer. A. Predict one of several possible class labels. B. Predict the numeric value of a continuous variable. C. Group data into clusters based on similarity. D. Determine if data belongs to a single class or not. The correct answer is A. Predict one of several possible class labels. Let's walk through why this is the correct choice. Multi-class classification is designed to predict a single label from 3 or more possible categories. For example, classifying a photo as a cat, dog, or bird is a multi-class problem because the model must choose one from several defined labels. Option B describes regression, not classification. If you're trying to predict a continuous value like temperature or sales revenue, you're dealing with a regression task, not classification. Option C is about clustering, which is an unsupervised learning method. Clustering doesn't use predefined labels. Instead, it finds natural groupings in the data based on similarity. Lastly, option D refers to binary classification. That's where you're just trying to decide between two outcomes, like yes or no, spam or not spam, not among multiple categories. So if your model needs to pick from multiple defined classes, multi-class classification is the tool for the job. For each statement below, indicate whether the answer is true or false. Average distance to the centroid is used to assess cluster compactness. True silhouette score ranges from 0 to 100. False. Maximum distance helps identify outliers within a cluster. True cluster evaluation requires known labels. False. Let's now walk through why each answer is correct or incorrect. The first statement is true. In clustering, compactness refers to how tightly grouped the data points are within a cluster. One way to measure this is by calculating the average distance of all points in a cluster to the centroid. Smaller values indicate more compact, cohesive clusters. Now, the second statement is false. The silhouette score, which is commonly used to evaluate clustering quality, actually ranges from -1 to 1. A score closer to 1 indicates well-separated, well-formed clusters, while values near or below 0 suggest poor or overlapping clustering. The third statement is true. Maximum distance within a cluster can highlight outliers, those data points that are much farther from the centroid than the rest. This helps identify if any values are straying too far from the typical behavior of the group. Finally, the fourth statement is false. Clustering is an unsupervised learning technique, which means it doesn't rely on known labels. Instead, it tries to uncover hidden structure or groupings in the data without any prior labeling. So overall, cluster evaluation focuses on internal metrics and doesn't depend on labeled outcomes, unlike supervised learning methods. Which technique is used to compare semantic similarity between token embeddings in transformer models? Select one answer. A. Jacquard similarity. B. Mean squared error. C. Cosine similarity. D. Gradient descent. The correct answer is C. Cosine similarity. Let's take a moment to understand why this is the best choice. Cosine similarity is commonly used in NLP to measure how similar two vectors are in terms of their direction. In transformer models, each token is embedded as a vector in high-dimensional space, and cosine similarity helps us assess how closely two token vectors align, essentially telling us if they carry similar meaning. Jacquard similarity, on the other hand, is useful for comparing sets, not continuous vectors. It's often used to measure overlap between groups, like sets of keywords or tags. Mean squared error is used in regression problems to measure the difference between predicted and actual numeric values, not to compare vector semantics. Finally, gradient descent is a training algorithm used to optimize weights during learning. It doesn't have anything to do with measuring similarity between embeddings. So, when it comes to comparing the semantic closeness of word embeddings, cosine similarity is the go-to method. Fill in the blanks by selecting the correct options from the drop-down menus. To prepare data for training, you should first extract it from the source, transform it into a suitable format, and load it into a serving layer. Now let's walk through each step of that process and understand why it's correct. First, you begin with extraction. This means pulling raw data from wherever it lives, maybe a database, a data warehouse, or a third-party system. Without this initial step, there's no data to work with. Once the data is extracted, the next step is to transform it. This is where cleaning, normalization, and formatting take place. Maybe you're converting timestamps, encoding categories, or handling missing values, whatever gets the data into a structure your training process expects. Finally, you load the transformed data into a serving layer or storage environment where it can be accessed efficiently by your machine learning pipeline. This completes the ETL process: extract, transform, load. Other options like scoring, deploying, or monitoring are part of later stages like model evaluation and operationalization, not data preparation. So ETL remains the foundational sequence for getting your data ready for training. What are two important factors to consider when selecting a machine learning training service? Select two answers. A, how much time you're willing to invest. B, whether the data is encrypted. C, whether the model is deployed to IoT devices. D, which programming language you're comfortable with. The correct answers are A, how much time you're willing to invest. D, which programming language you're comfortable with. Let's walk through the reasoning behind these selections. First, the time you're willing to invest is a major factor. Some training services provide AutoML tools or simple APIs that allow quick model creation, perfect for fast deployment or beginners. Others demand deep customization, code-heavy workflows, or tuning, which means more time and effort from your side. Next, your familiarity with a programming language is also key. Many platforms like Azure ML or Databricks support a range of languages such as Python, R, or Scala. Choosing a service that aligns with your language skills makes development smoother and more productive. On the other hand, data encryption is critical for security, but isn't something that typically impacts the selection of a training service. It's a general requirement across all services, not a differentiator for training features. Lastly, deployment to IoT devices comes into play after the training phase. It affects how you operationalize the model, not how you train it. So it's not a selection factor during service evaluation. So when selecting a training service, think about your time investment and the coding tools you're most comfortable using. For each statement below, indicate whether the answer is true or false. Azure Machine Learning Studio lets you import models from a model catalog. True. Compute selection in Azure ML is always static and predefined. False. Spark Compute allows for distributed training but requires script changes. True automated ML does not support natural language processing tasks. False. Let's go ahead and break down each of these statements. First, it's true that Azure Machine Learning Studio lets you import models from a model catalog. This feature allows you to reuse pre-trained models or integrate externally developed ones, making your workflows more efficient. Next, compute selection in Azure ML is not always static and predefined. That statement is false. In practice, compute decisions are often made dynamically depending on performance, cost, and resource availability. So, users commonly tweak settings over time. The third statement is true. Spark Compute does allow for distributed training, which is great for handling large datasets. However, it typically requires you to adjust or rewrite your training scripts to enable distributed execution correctly. Finally, the idea that automated ML doesn't support natural language processing is false. In reality, AutoML in Azure supports various NLP tasks, such as text classification, using no-code interfaces or configurable pipelines. So overall, Azure ML provides a flexible environment with strong support for both traditional and advanced machine learning tasks, including NLP and distributed computing. Which two statements describe valid use cases for batch predictions? Select two answers. A, you want to score a folder of images at once and store results in a file. B, you want to instantly predict product recommendations when a user clicks an item. C, you want to score multiple customer records in a single table upload. D, you want the model to return a response during the page load time. The correct answers are A, you want to score a folder of images at once and store results in a file. C, you want to score multiple customer records in a single table upload. Let's walk through the explanation to clarify this. Batch predictions are ideal when you need to process a large volume of input data all at once, rather than making predictions one at a time. For instance, scoring a folder of images and saving the results to a file is a perfect use case. You can submit all the images together, and the system will generate predictions in bulk and store them for review. Similarly, uploading a table of customer records to score all at once is a textbook batch use case. You're not waiting on immediate feedback. You just want all the entries processed and results turned after the job finishes. On the flip side, predicting product recommendations when a user clicks on an item is a real-time use case. It requires immediate prediction and feedback, not batch handling. The same applies to returning a model response during page load. These are latency-sensitive tasks that rely on fast, low-latency predictions, better handled by real-time inference, not batch processing. So when you're working with batch predictions, think in terms of bulk processing jobs, not immediate responses. For each step in the machine learning process, drag it to the appropriate description in the correct match column. Decide what the model should predict and define success criteria. Define the problem. Import and inspect the dataset. Load data. Normalize and clean for consistency. Pre-process data. Select and configure an algorithm. Choose model. Learn patterns from the training data. Train model. Generate predictions on test data. Score model, calculate performance metrics. Evaluate. Let's walk through each step and see how they fit into the overall machine learning pipeline. First, defining the problem is where it all begins. You identify what you want the model to predict. Maybe it's customer churn or product demand, and how you'll measure success, like using accuracy or F1 score. Next, loading the data means pulling in the dataset you plan to use. This is often from files, databases, or cloud sources. Once loaded, you inspect it for completeness and structure. Then comes pre-processing. This is where you clean the data, normalize values, handle missing entries, and get everything ready for training. Think of it as setting the table before a meal. Everything needs to be in place. Once the data is ready, you choose a model. That means selecting an algorithm, maybe a decision tree, logistic regression, or neural network, and configuring its settings. With the model selected, it's time to train. This is when the algorithm learns from the labeled training data, finding patterns and relationships it can use to make predictions. After training, the model is tested. It generates predictions on a test dataset, and this is known as scoring the model. Finally, you evaluate performance. This means calculating metrics like precision, recall, or RMSE to understand how well your model is doing. Notice that items like use GPU resources or write raw SQL queries don't belong here. Those may support the process, but they're not core steps in the machine learning lifecycle. So the flow is define, load, clean, choose, train, score, and evaluate. That's the heartbeat of every ML project. For each statement below, indicate whether it is true or false. The quality of generative AI output depends solely on the language model used. False prompt engineering is the process of improving AI prompts for better results. True system messages define how the model behaves and responds. True, clear, specific prompts improve the usefulness of AI responses. True. Now let's take a moment to explain why these are the right answers. The first statement is false. While the language model does play a significant role in output quality, it's not the only factor. Prompt clarity, user intent, context, and even formatting all influence the final result. A powerful model can still produce poor output if it's given a vague or poorly structured prompt. The second statement is true. Prompt engineering is all about refining and crafting input prompts to guide the AI toward more accurate or relevant responses. It's a technique used to improve performance, particularly in zero-shot or few-shot learning setups. The third statement is also true. System messages, which are part of the system prompt, help define the AI's behavior, tone, and boundaries. They're useful for aligning model output with specific tasks or user expectations. And lastly, the fourth statement is true as well. Clear, specific prompts almost always lead to better responses. When the model knows exactly what you're asking, it can generate more accurate and context-aware answers. So effective AI interaction isn't just about having a great model, it's also about how you guide it. Fill in the blanks by selecting the correct options from the drop-down menus. Artificial intelligence, AI, interacts with its environment and executes tasks without explicit output instructions. Let's break down why these are the correct choices. First, interacting with its environment is one of the core traits of AI. It means AI systems can receive data from sensors, users, or systems around them, and then use that input to make decisions or take actions. Think of self-driving cars responding to traffic conditions or smart assistants adjusting to your preferences. Second, AI executes tasks without explicit output instructions. This is what makes AI intelligent. It can infer what to do based on patterns in the data, rather than being told every step. For example, a recommendation engine doesn't need to be told what movie to suggest for every user. It learns from past behavior and makes its own predictions. In contrast, storing files, relying on hard-coded rules, or using static templates are characteristics of traditional software, not AI. AI systems are dynamic, adaptable, and can generalize to new situations beyond predefined scripts. So, together, these two traits define AI's flexibility and intelligence. It learns from its environment and acts with autonomy. Which two components are part of the original transformer architecture? Select two answers. A. Decoder, B. Encoder, C. Softmax vectorizer, D. Gradient predictor. The correct answers are A. Decoder, B. Encoder. Let's go through why these two are correct. The original transformer architecture, as introduced in the paper Attention is All You Need, is built on two main components, the encoder and the decoder. The encoder takes in the input sequence and converts it into a set of representations that capture meaning and context. These representations are then passed to the decoder. The decoder's role is to take those encoded representations along with previously generated outputs and produce the final output sequence, often in tasks like translation or summarization. Together, these two blocks allow the model to process and generate complex sequences. Now, Softmax vectorizer might sound technical, but it's not an actual structural component. Softmax is just an activation function used within the attention mechanism to help assign weights. It isn't a standalone module. And gradient predictor? That's not a real component in transformer design either. Gradients are part of training algorithms like backpropagation, but there's no such thing as a gradient predictor in this architecture. So if you're studying how transformers work, remember everything starts with the encoder-decoder structure. A software team needs a generative AI model that can run locally on edge devices and be fine-tuned quickly for use in a medical diagnostic chatbot. What type of model should they consider using? Select one answer. A. Large language model, LLM. B. Small language model, SLM. C. Open source model from an online catalog. D. Proprietary model with general purpose training. The correct answer is B. Small language model, SLM. Let's talk through why this is the best choice. Small language models are designed for scenarios where compute resources are limited, like edge devices. They're faster to fine-tune and more lightweight, which makes them ideal for specialized tasks such as medical diagnostics. SLMs are also often trained on domain-specific data, so they can deliver more relevant results out of the box compared to general-purpose models. Large language models, by contrast, are powerful but heavyweight. They require significant compute resources to run and fine-tune, making them a poor fit for local edge deployment where speed and efficiency matter. An open-source model might sound appealing, but its availability doesn't necessarily mean it's optimized for small-scale domain-specific use. You'd still need to consider the model size and training scope. Finally, a proprietary general-purpose model is often designed for cloud-scale use and broad applications, not for quick, fine-tuned deployment in a narrow medical context. So for edge-based, fast-adapting AI, SLM is the way to go. Fill in the blanks by selecting the correct options from the drop-down menus. Azure AI Foundry gives developers full control over model customization and deployment, while Copilot Studio is a fully managed solution where infrastructure is automatically handled for you. Let's unpack what this means and why it's the correct distinction. Azure AI Foundry is designed for flexibility and customization. It gives developers full control, meaning they can configure the environment, fine-tune models, and manage deployment specifics. This is ideal for organizations that need tailored solutions or want to experiment with different architectures and parameters. On the other hand, Copilot Studio is a fully managed platform. This means Microsoft takes care of all the infrastructure behind the scenes, like scaling, hosting, and resource allocation. You just focus on building your app or automation without worrying about what's going on under the hood. Options like low permission, community-driven, or CLI-based might describe certain tools or preferences, but they don't reflect the core difference here, which is all about control versus convenience. So if you're choosing between these two, the key trade-off is, do you want hands-on customization or a simplified managed experience? When you create a hub in Azure AI Foundry, which two things become available for AI solution development? Select two answers. A. Azure AI Services. B. Power BI dashboards. C. GitHub Copilot. D. Microsoft Stream. E. Azure Machine Learning. The correct answers are A. Azure AI Services. E. Azure Machine Learning. Let's walk through why these two are correct. When you create a hub in Azure AI Foundry, it activates a workspace that integrates several tools for building AI solutions. Azure AI services, such as speech, language, vision, and content safety, are part of that setup, enabling you to bring intelligence directly into your apps. Azure Machine Learning is another major component. The hub links directly with Azure ML to help you build, train, and deploy machine learning models within that development environment. Now, Power BI dashboards are great for visualizing data, but they're analytics tools, not core components of an AI Foundry hub. GitHub Copilot is a coding assistant that suggests lines of code, but it's not part of the Azure AI Foundry experience. Similarly, Microsoft Stream is focused on video content, not AI model development or training. So if you're setting up a development environment in AI Foundry, Azure AI Services and Azure Machine Learning are your foundational building blocks. For each statement below, indicate whether the answer is true or false. Groundedness measures how consistent the response is with context. True, relevance, determines how well the response matches the original query. True fluency checks for harmful or inappropriate language. False coherence evaluates the logical flow and consistency of responses. True. Let's walk through each one to clarify why these are the correct answers. Groundedness is true. This metric tells us whether the response aligns with its source material or context. It's essential for evaluating if an AI-generated answer is sticking to factual grounding rather than making things up. Relevance is also true. It assesses how well the generated response addresses the user's original question or intent. If a model veers off topic, it loses relevance, even if the answer is fluent or grammatically correct. The third statement is false. Fluency refers to how readable and natural sounding the response is, not whether it includes harmful content. Safety checks for harmful or inappropriate language fall under a separate evaluation category, often referred to as toxicity or harm. Finally, coherence is true. This evaluates how well the response logically flows from sentence to sentence. A coherent answer should be easy to follow and internally consistent. So when evaluating AI outputs, it's not just about accuracy, it's about how well everything fits together: relevance, groundedness, fluency, and coherence. Fill in the blanks by selecting the correct options from the drop-down menus. Before tokenization, text normalization may be used to remove punctuation and standardize casing. When extracting meaningful information, stop word removal helps by ignoring common words like the or it. Let's break down why these answers are correct. Text normalization is an important pre-processing step that makes text consistent for analysis. It usually involves lower casing all letters by removing punctuation, expanding contractions, and sometimes even fixing misspellings. All of this helps make sure that variations in how words are written don't affect downstream analysis. Then we have stop word removal. This step filters out commonly used words that carry little meaning on their own, like the, is, in, and it. By removing these, the focus shifts to more meaningful terms that actually influence interpretation, such as diagnosis, alert, or approval. Now, other options like n-gram generation or stemming serve different purposes. N-grams help in analyzing phrases or sequences, not cleaning the text. And stemming simplifies words to their root forms, but it doesn't eliminate common ones. Entity recognition doesn't modify the text either. It's about labeling key terms after the pre-processing is done. So for a clean and focused input before model processing, normalization and stop word removal are your go-to techniques. Natural language processing has historically been a challenge in AI because select one answer. A. Computers cannot handle numeric data effectively. B. Most text is stored in structured formats. C. Human language is highly complex and ambiguous. D. Tokenization is not yet a solved problem. Let's walk through the explanation now. To begin with, the correct answer is C. Human language is highly complex and ambiguous. This is the core reason why natural language processing, or NLP, has been historically difficult. Language is full of nuance. Words can have multiple meanings, tone can shift context, and sentences can vary widely in structure. For instance, the word light could mean brightness or something not heavy, depending on context. Teaching machines to handle this ambiguity is not straightforward. Now let's look at the incorrect options. Option A, computers cannot handle numeric data effectively, is actually not true at all. Numeric processing is a strength of traditional computing systems. It's text and language that pose challenges. Moving on to option B, most text is stored in structured formats. That's also incorrect. In fact, most text data exists in unstructured formats like emails, social media posts, and articles, exactly the kind of content that NLP is designed to understand. Finally, option D says tokenization is not yet a solved problem, which is misleading. Tokenization, splitting text into words or phrases, is a well-established NLP technique. While language as a whole is complex, tokenization itself is a solved process within that broader challenge. So once again, the main issue is the complexity and ambiguity of human language. You're developing a basic spam filter that needs to classify emails as spam or not spam based on certain keywords. You want a technique that has historically been used for this task and can identify word groups common in spam messages. Select one answer. A, TF-IDF. B, naive Bayes. C, stemming. D, entity recognition. Let's go through the explanation now. The correct answer is naive Bayes. This is a classic statistical model that has been widely used for spam filtering. It works by analyzing the frequency of words in spam versus non-spam emails, and then calculating the probability that a message belongs to a particular class, spam or not, based on those word patterns. For example, if words like free, winner, or click appear frequently in spam emails, the model learns to associate those patterns with spam classification. Now, TF-IDF, while useful in information retrieval and search engines, isn't ideal for binary classification tasks like spam detection. It ranks word importance in documents but doesn't classify them. Next, stemming helps simplify words to their root forms, like turning running into run, but it doesn't classify messages. It's just a pre-processing step. Lastly, entity recognition identifies names, locations, or dates within text, which doesn't help with spam classification based on word frequency. So overall, naive Bayes is the technique best suited for this task due to its simplicity, effectiveness, and proven track record in spam detection. For each statement below, indicate whether the answer is true or false. Entity recognition supports subtypes like percentage, ordinal, and temperature. True summarization rewrites text to make it more creative. False PHI is a type of sensitive information identified by the PII detection feature. True. A detected email address is considered an entity. True. Let's go through the explanation now. First, entity recognition can detect various subtypes beyond just names or dates. It includes things like percentages, ordinal values, and temperature readings. This makes it useful in domains like finance or science where such details matter. On the other hand, summarization isn't designed to make content more creative. Rather, it condenses text by highlighting the most important points, which helps users quickly understand key insights from long documents. Next, PHI, or personal health information, falls under the broader category of PII, personally identifiable information. AI models with PII detection capabilities are trained to spot things like health data, making this statement true. Lastly, a detected email address is indeed considered an entity in Azure AI language models. These tools treat identifiable items like emails, phone numbers, and names as entities to help with classification and protection. So overall, 3 of these statements are true and 1 is clearly false based on its intended function. What does the custom question answering feature in Azure AI language allow you to do? Select one answer. A, automatically summarize chat history into a support ticket. B, create and query a knowledge base using natural language. C, train a chatbot to recognize facial expressions during conversation. D, translate customer questions into multiple languages. The correct answer is B, create and query a knowledge base using natural language. Let's go through the explanation now. The custom question answering feature in Azure AI language enables users to build a knowledge base from documents like FAQs and query it using natural language. In other words, it understands questions phrased in everyday language and retrieves answers directly from that content. Now, why are the others incorrect? First, option A refers to summarization. While Azure does support summarization, it's a separate function from question answering and doesn't involve querying a knowledge base. Next, option C is about recognizing facial expressions, which falls under vision-related services. Azure AI Language doesn't deal with visual input. Lastly, translation capabilities, as mentioned in option D, are handled by Azure Translator, not the question answering feature. So overall, if your goal is to let users ask questions in natural language and get answers from a structured source like FAQs or manuals, this feature is exactly what you need. Which statement best describes how conversational AI differs from generative AI? Select one answer. A. Conversational AI models use facial recognition to analyze emotion. B. Conversational AI creates original stories and poems from scratch. C. Conversational AI handles dialogue between humans and AI. D. Conversational AI performs image captioning and alt text generation. The correct answer is C. Conversational AI handles dialogue between humans and AI. Let's go through the explanation now. Conversational AI is all about interpreting and responding to natural language in a dialogue setting. For instance, think of virtual assistants like chatbots or customer support agents. They're designed to understand what you say and reply meaningfully. Now, the first option about facial recognition and emotion belongs more to visual AI, not language-based conversational AI. Then we have the second option, creating original stories or poems, which is a hallmark of generative AI, where creativity is the goal rather than conversation flow. Lastly, image captioning and alt text generation again fall into the realm of computer vision tasks, not conversation. So when you're comparing the two, just remember, conversational AI talks with you, generative AI creates for you. You are developing an app that uses Azure AI Speech and several other Azure AI services, such as Vision and Language. You want to manage access and billing for all these services together. Which resource type should you create? Select one answer. A. Azure AI Services Resource. B. Speech Resource. C. Cognitive Services Multi-Account. D. Azure Container Instance. The correct answer is A. Azure AI Services Resource. Let's go through the explanation now. When you're working with multiple Azure AI services, say combining vision, speech, and language, it makes the most sense to use a unified resource that can manage them all. That's where the Azure AI Services resource comes in. It lets you bundle those services together, simplifying both access management and billing. Now, if you chose the speech resource, that's not wrong in terms of functionality, but it's more suitable when you're only using Azure AI Speech on its own, not alongside other services. As for cognitive services multi-account, it may sound valid, but it's not an actual resource type in Azure. Finally, Azure Container Instance is used to host containers, not to manage AI services, so that doesn't apply here. So remember, if you're integrating multiple AI capabilities, go with Azure AI Services Resource. For each statement below, indicate whether the answer is true or false. Speech Studio provides a graphical interface for building speech applications. True. The Azure AI Speech CLI is the only way to use speech services. False. The SDKs and REST APIs allow developers to integrate speech into apps programmatically. True. A speech resource must be used if you plan to combine speech with other AI services. False. Let's go through the explanation now. First off, Speech Studio does offer a graphical interface, making it easier for users to build, test, and refine speech features without writing code. It's a UI-based tool designed for accessibility and quick experimentation. However, the claim that the CLI is the only way to use speech services is incorrect. In reality, developers have multiple options, including SDKs, REST APIs, and even Speech Studio itself. So CLI is just one method, not the only one. Next, it's true that SDKs and REST APIs are the preferred tools when integrating Azure AI Speech into your own apps. They allow for fine-grained control and automation, ideal for developers building real-world solutions. Finally, if you're combining Azure AI Speech with other services like Vision or Language, a speech resource alone won't be sufficient. You'd actually use an Azure AI Services resource instead, which is designed for bundling multiple AI capabilities under a single resource. This combination ensures easier management, unified billing, and streamlined access control. For each statement below, indicate whether the answer is true or false. A pixel value of 0 in a grayscale image represents black. True. Grayscale images use the RGB model with reduced colors. False. In grayscale, pixel values of 128 appear as medium gray. True grayscale images require 3 color channels to store pixel data. False. Let's go through the explanation now. Starting with the first statement, it's true that a pixel value of 0 in a grayscale image indicates black. Grayscale images work on a scale from 0 to 255, where 0 is black and 255 is white. Next, the idea that grayscale images use the RGB model is false. Unlike color images, grayscale images use a single channel model, which stores intensity values only, not separate red, green, and blue values. Moving on, a pixel value of 128 does indeed represent a medium gray. This is because 128 is about halfway between 0 and 255, giving you a balanced, mid-range shade of gray. Lastly, it's incorrect to say that grayscale images require 3 channels. Unlike RGB images that use 3 separate color channels, grayscale images only need 1 channel to store their intensity values. So overall, grayscale simplifies image data by focusing purely on brightness levels, not color. A quality control engineer wants to highlight surface cracks on metal parts by enhancing the edges in images captured on the production line. They decide to apply a convolutional filter using a 3x3 kernel that emphasizes high contrast transitions. Which resource type should you create? Select one answer. A Gaussian filter will best detect cracks. B, a Laplace filter is suited for edge detection like cracks. C, a color inversion filter will help visualize defects. D, an RGB filter will isolate the crack color channel. The correct answer is B. A Laplace filter is suited for edge detection like cracks. Let's go through the explanation now. First, a Gaussian blur filter smooths the image, reducing noise and detail, which softens edges. Therefore, instead of enhancing cracks, it makes them less visible, so it's not the right choice. Next, a Laplace filter is designed specifically to enhance regions with rapid intensity changes. These sharp transitions in pixel values are characteristic of edges and cracks, making Laplace filters highly effective for detecting such defects. On the other hand, a color inversion filter simply reverses color values but doesn't enhance edges. This might make defects look different but doesn't help isolate or emphasize them. Finally, an RGB filter focuses on isolating specific color channels. However, surface cracks are not necessarily tied to a specific color and usually don't benefit from color filtering alone. So for detecting fine, high-contrast features like cracks in industrial images, the Laplace filter is the most effective tool. You are building an image captioning system using a modern AI model. You want the model to understand both the image and related text to generate accurate captions. Which type of model is most suitable for this task? Select one answer. A multimodal model combining image and language encoders. B, a CNN trained only on labeled object categories. C, a transformer model trained purely on token sequences. D, a GAN model used for image generation. The correct answer is A, a multimodal model combining image and language encoders. Let's go through the explanation now. To begin, a multimodal model is trained to understand both visual and language data. This means it can align image features with language representations, making it ideal for generating accurate captions that reflect what's seen in the image. Meanwhile, a CNN trained only on labeled object categories can classify what's in an image but lacks the ability to describe it using natural language, so it falls short for captioning tasks. Likewise, a transformer model that's trained purely on text sequences is powerful for language tasks, but it doesn't process visual inputs. This makes it unsuitable when image understanding is required. Lastly, GANs are primarily used for generating new images rather than interpreting existing ones. They don't have the architecture necessary to link image data to language output. So when both image comprehension and language generation are needed, a multimodal model is clearly the best fit. For each statement below, indicate whether the answer is true or false. Azure AI Vision is a cloud service based on deep learning models. True computer vision cannot be used to unlock personal devices. False. Azure AI Video Indexer is built by combining multiple Azure AI services. True computer vision is limited to image analysis only and cannot be used in videos. False. Let's go through the explanation now. To begin with, Azure AI Vision is indeed a cloud-based service that uses deep learning to power image and video analysis. It provides both pre-built models and customizable ones, making it suitable for a range of tasks like object detection, OCR, and facial recognition. Next, the idea that computer vision cannot be used to unlock personal devices is incorrect. In reality, facial recognition, a major application of computer vision, is commonly used in smartphones and laptops for secure access. Moving on, Azure AI Video Indexer is a powerful tool that combines several Azure AI services. It doesn't just analyze visuals, it also integrates speech recognition, translation, and facial detection to make video content searchable and insightful. Lastly, it's not true that computer vision is limited to still images. On the contrary, services like Azure Video Indexer allow computer vision to process and extract insights from video streams, which is especially useful for media companies or security monitoring systems. What is one major benefit of implementing AI vision systems in business operations? Select one answer. A. They eliminate the need for all manual labor. B. They enable audio transcription at scale. C. They automate time-intensive tasks and enable new possibilities. D. They replace the need for human supervision in all systems. Let's go through the explanation now. First of all, the correct answer is option C. AI vision systems are most valuable when they automate repetitive and time-consuming tasks, like quality inspection on a production line or counting inventory in a warehouse. This allows businesses to save time and unlock new operational capabilities that wouldn't be possible with manual processes alone. Now, although option A sounds promising, AI vision doesn't eliminate all manual labor. It assists and enhances human work, but doesn't completely remove the need for people, especially for complex decision-making or tasks requiring judgment. Next, option B talks about audio transcription, which is actually handled by speech-to-text AI, not AI vision systems. These are separate areas of artificial intelligence and shouldn't be confused. Lastly, option D suggests that human supervision is no longer necessary. In reality, human oversight remains crucial, especially in sensitive applications like healthcare, safety monitoring, or autonomous systems. AI is a tool, not a total replacement. So in business, the true power of AI vision lies in boosting productivity while enabling innovative ways to operate. What does the term knowledge mining refer to in the context of AI-powered information extraction? Select one answer. A. The process of extracting handwritten notes from scanned images. B. Using AI to summarize call recordings. C. Tagging and enriching content to enable search and discovery. D. Translating customer emails into structured tables. The correct answer is tagging and enriching content to enable search and discovery. Let's go through the explanation now. Knowledge mining focuses on using AI to extract metadata from unstructured content and apply tags, making that content easier to search and analyze. For example, imagine scanning hundreds of documents and instantly being able to find which ones reference a specific product or contain legal terms. That's knowledge mining in action. It adds structure and discoverability to raw data. On the other hand, extracting handwritten notes from scanned images refers specifically to OCR, or optical character recognition. While useful, it's a narrower task and not representative of knowledge mining as a whole. Similarly, using AI to summarize call recordings is a speech-to-text or audio summarization task. It doesn't include the tagging or discovery aspects that define knowledge mining. And translating emails into structured tables may sound like enrichment, but it's actually part of a transformation workflow. It doesn't inherently involve tagging for search or discovery. So in business contexts where teams need to surface insights from thousands of files, knowledge mining becomes a powerful solution through tagging and enrichment. Fill in the blanks by selecting the correct options from the drop-down menus. Each extracted field in a form is assigned a confidence score, which is a decimal value between 0 and 1, indicating how accurate the extraction likely is. Let's go through the explanation now. A confidence score tells us how reliable an AI model thinks a specific extraction is. For instance, if a form field is read as invoice number 4783 and the model assigns a score of 0.98, it means the system is almost certain it captured that value correctly. Now, the scale is important. Confidence is always expressed as a decimal between 0 and 1. The closer the score is to 1, the more confident the model is in its result. Other options like a syntax label or string value might seem relevant but serve different purposes. Syntax labels are for grammatical tagging, and string values simply indicate data types, not confidence. Likewise, bounding box and OCR layer relate to where content is located or how it was extracted visually, but don't tell us how sure the model is about the data's accuracy. So remember, when you're assessing extraction reliability in AI form processing, look for the confidence score between 0 and 1. For each statement below, indicate whether the answer is true or false. Field descriptions define what a field name represents semantically, true. The field value provides the label or category for the data, false. Bounding box coordinates help models associate text with spatial position in documents, true. Coordinates like 4.1, 2.2 refer to pixel values for coloring scanned forms, false. Let's go through the explanation now. First, field descriptions are indeed used to explain the meaning or context of a field name. For example, a field called due date might have a description that clarifies it refers to the deadline for payment, helping models and users interpret data more accurately. Next, the idea that the field value provides the label is incorrect. The label or category is the field name itself, while the value is the actual content being extracted, like John Smith, being the value for a field named customer name. Now, bounding box coordinates are essential in document analysis. They help the model figure out where each piece of text is located on a page. So if the label is in the top left and the value is in the top right, the model uses spatial data to link them. Finally, while 4.1, 2.2 looks like it could represent a pixel color value, in this context, it's actually describing spatial position, part of a bounding box used to outline text, not to define colors. So overall, understanding how fields, values, and coordinates interact is key to accurate AI-powered information extraction. A company uses two different invoice formats. One uses vendor name, the other uses supplier. They want to extract this information using one unified analyzer. Which feature of Azure AI Content Understanding enables this capability? Select one answer. A, the ability to create multilingual labels. B, support for traditional OCR workflows. C, schema-based extraction with label mapping flexibility. D, manual review and tagging for each field. The correct answer is schema-based extraction with label mapping flexibility. Let's go through the explanation now. To begin with, schema-based extraction with label mapping flexibility allows Azure AI Content Understanding to identify and extract the same data field even when it's labeled differently across documents. For instance, vendor name and supplier can both be mapped to a single schema field like company name, allowing the analyzer to unify extraction without confusion. Meanwhile, although multilingual labels are supported by Azure, that feature alone doesn't enable this kind of mapping flexibility. It's more about handling input in various languages, not interpreting label equivalents. Moving on, traditional OCR simply reads text as it appears visually, but it doesn't understand context or relationships between different labels and data fields. So while it's foundational, it's not sufficient for this task. Finally, manual review and tagging is a fallback method that requires human input, which schema-based extraction is designed to reduce or eliminate altogether. So in summary, the power of schema-based extraction lies in its ability to flexibly match data fields across formats, making it the best fit for companies dealing with document variation. For each statement below, indicate whether the answer is true or false. Azure AI Content Understanding can extract data from both still images and recorded video. True, only video files support schema-based extraction. Still images do not. False, video analysis enables time-based insights, such as attendance over time. True, still image analysis can identify participants and locations in a single snapshot. True. Let's go through the explanation now. First, it is true that Azure AI Content Understanding can work with both still images and recorded video. This versatility enables organizations to analyze documents, forms, and other content captured in different media formats. However, the second statement is false. Schema-based extraction is not limited to video files. It can also be applied to still images. So saying that only video supports it is incorrect. Moving on to the third statement, it is true that video analysis enables time-based insights. Because video is a sequence of frames over time, it can reveal patterns like changes in attendance, movement, or engagement levels. Lastly, the fourth statement is also true. Still image analysis is capable of identifying participants and spatial context from a single frame, such as who is present in a meeting room or where people are located. So overall, this question highlights the breadth of capabilities in Azure AI Content Understanding, especially when working across both image and video content types. Fill in the blanks by selecting the correct options from the drop-down menus. Azure AI Content Understanding allows you to define custom schemas that work across text, audio, image, and video content. These schemas define fields to extract regardless of how or where the data appears. Let's go through the explanation now. First, Azure AI Content Understanding enables you to define custom schemas, which means you can tailor the extraction process to specific business needs. These schemas aren't predefined. They're flexible and designed to match the structure of your unique data sources. Next, those schemas define fields. That is, the pieces of information you want to extract, like names, dates, actions, or locations. It doesn't matter whether the source is audio, video, or an image file. The system uses the same schema logic to locate and extract those values. Now, while things like tags, captions, and subtitles may be useful in media, they aren't what drives schema-based extraction. Similarly, OCR labels or file extensions are irrelevant in this context. They don't define what to extract. So in practice, if you're processing customer feedback from both emails and call transcripts, you can use the same schema to extract sentiment and names from both formats. That's the power of using custom schemas and clearly defined fields.